the language of the universe.
But I don't understand it.
Hello, everybody. Welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you back to episode number 99, where today we have Professor Sara Seager on here with us, an exoplanetary scientist currently teaching at MIT. So, Dr. Seager, maybe you want to introduce yourself a little bit to our audience?
Hi, I'm Professor Sara Seager. I actually was born and grew up in Toronto. And in fact, I live just a few blocks away from the downtown University of Toronto campus. So that's where I did my undergrad. And eventually I moved to the United States. And now I'm an exoplanet astrophysicist at MIT, as Ray already said. And I love exoplanets, and the thought of exploring these planets using telescopes is what I love doing.
That's fantastic. Before we actually do get into the podcast, as you guys know, we have the comment of the week.
Awesome comments. I actually loved a lot of the comments that were portrayed this week. Every week that happens. But this particular week, the comment of the week goes to Paul Smith. He states, "I'm guessing you have a lot of freshman physics majors watching your show. I am actually a 54-year-old freshman astrophysics student, and I love it. As someone trying to get back to school at this age, I find it helpful to listen to a couple of fellow students who are going through these topics in a couple of years ahead of me. Keep it up." So,
thank you so much, Paul.
Thank you so much,
for
Paul.
your fantastic comment. If you want to be next week's comment of the week, make sure to come to the YouTube channel under this video and leave a comment, and you might get chosen for next time.
Super simple. I think without any further delay, we can get straight into the podcast. And as all of you know, the classic question begins. So, Professor Seager, let me ask you, how did you get into this field of planetary science? Take us from the back.
Part of it's luck, part of it's timing. But I always loved astronomy ever since I was a small child. I don't know if you two have had this, but I always remember the moon, looming large. And I have this distinctive memory of being in the car with my dad, and the moon just kept following us. It must have been a full moon. Like, no matter how far we went or where the car turned, it was just always there. And I remember specifically asking my dad, why? Why is the moon following us? And we could sort of put that out to the audience to think about for a minute. I don't think my dad answered that, actually. You know what it is? It's just so far away that it just appears to be fixed in its position. Mm-hmm. So I love the moon. I was so lucky I got to see the dark night sky. Have you two seen that? Like, truly dark sky?
Yeah.
I think once it was like those camps, whenever you go for those camps in those really northern places, I think those are the only real places.
Exactly.
But I think
and you have to get lucky though, right? Because it would have to be
for
night
sure.
without a full moon, and the what we call scene has to be good. Because one time, my family and I, we went to New Hampshire. That's like a few hours north of Boston, and we went to look for, it's like northwest. We went to see the Perseids, and we woke up in the middle of the night and went out. And there weren't any clouds, but it also at the same time wasn't clear. And we realized we could see the stars, but not very well. And we realized it was so humid, that it really ruined our dark night sky. So you have to be lucky, right? Maybe it's just the summers in Ontario or something, but that's what I got to see too. And it always kind of stayed with me. Then when I was older, I actually went to University of Toronto, but my dad said I had to be a doctor. I know there's a lot of listeners who are going to be with that, right?
Yeah,
because
100%.
when you tell your parents you want to be an astronomer, they don't get that. And now that I'm a parent myself, I can tell you why. Because you want your kid to get a job and support themselves.
Right.
Okay?
That's a way to say
it. None of your parents want to see you. Like, they either need you to make money so you can support them, or if they have enough money, they don't want to be paying for you. So it doesn't matter, like, wherever they're at. So, a lot of parents, they don't realize that if you train to be an astronomer, you'll always have a job. Maybe not in astronomy, but, think of the world around us. Data science is everything, right? Like, when you order on Amazon and they might already know what you want. They suggest things. Yeah. So, like, understanding data, being able to manipulate computer programs, all of that is really good training for any job. And in fact, when I started at the University of Toronto, that's what they told us. We were studying physics. They're like, you can always get a job. I mean, they might have not said it that way, but they said, like, the unemployment rate among physics graduates is basically zero. So that was heartening. Right. So I entered the university to study Premed. Oh my gosh. Do you ever see those physics classes for Premed? And they're just so full of people.
No.
You don't know. You should
Never.
maybe like, you know, just sort of, yeah, tons of physics for Premed. But I decided not to do that. I decided that I really loved astronomy. And when I realized I could be an astronomer for a job, it was a really great thing. And I was able to get a summer internship. I don't know what they call them nowadays at the university, but I did that at the David Dunlap Observatory, which
Right.
back then was still a research institute. Yeah.
Oh wow.
Yeah, so I think we applied maybe for the same research program. It's called SERP now, like the
Okay.
Summer Undergraduate Research Program at the Dunlap Institute.
Nice.
That's so cool. Yeah, so it's
Yeah,
actually
this is
been
something else
coming
now
through the
because
years.
do you know about the David Dunlap Observatory?
Yes, yes.
Yeah. So eventually they sold it and that money went to found the Dunlap Institute.
Oh, okay.
Oh, is that how it happened? Because it's actually very
Yeah.
nearby Richmond Hill, where I
Yeah, I
actually
definitely,
reside.
yeah, I
Where
encourage you
used
to,
live.
to
Yeah.
you and everyone listening to look up the history because a long, long time ago, I think this was in the 1920s, there was like nothing out in Richmond Hill. It was just like farmland. But the hill is so high, you can see all the way down to Lake Ontario. I mean, I don't know if you can tell there's a lake there, but you can like see the CN Tower. It's a
Yeah,
great
it's
place.
beautiful. It's beautiful
for
from there.
astronomy.
It's definitely beautiful.
And so David Dunlap, his widow, donated the money to build the observatory. And it's a really big telescope. It's like 2-meter mirror in diameter.
Wow.
And this thing kind of went on for a really long time as like a premier research institution. But as you know from living in Toronto, like the skies are not great over there.
Not at all.
And so, as people invested more and more in astronomy, they went further away, like Chile and other places where the weather's good. So eventually they wanted to sell it. But when they had founded the observatory, the stipulation was you can't sell it or all the money goes back to the family.
Oh, yeah.
Oh,
And so I'm not sure of the exact story, but you can imagine as the years went by, the land became worth more and more, like tens
Definitely.
of millions or more, 100 million probably, I don't know, huge amount. And eventually, as more generations went by in the Dunlap family, I don't know if this is exactly right, okay? So I was going to say, don't quote me on this, but eventually everyone came to an agreement. And so that's the money that went to the Dunlap Institute. And now the observatory, it's a outreach. It's used for outreach now.
wow. That's kind of a story for an institution, or at least for a current institute. That's really cool.
Sometime everyone should go out there because it's still a beautiful place.
I mean, can you still, I would still say, even in Richmond Hill, because I used to actually be a part of like an astronomy club in my school in Richmond Hill.
Okay.
And it was still not crazy good. Like it was still like you still had to go at least 2 hours up north to really see some stars. Like, what was your experience like in U of T? Were you actually looking at anything? Could you look at anything back then, or?
Yes, well, the suburbs were already all built up then. But think about when it was first built, there was like nothing there. But you can still see stars with a telescope. I mean, the telescope was 24 inches. The mirror was 24 inches in diameter. And we monitored bright variable stars. So you can definitely still see things. I mean, not every night when it's cloudy and everything. But,
Okay, so that's pretty wonderful. So that was your process through U of T. So you're kind of a student in U of T, and I'm still very intrigued into this medical to astronomy, because did you just tell your father that no, I'm gonna study astronomy?
Well, a couple of things happened. One is he also raised me to be very independent. So I think that backfired a bit. But there's a key thing that actually happened. I think I was still in high school at the time. I'm not quite sure remembering it right, but my parents were divorced since I was very young. And my dad, he's not alive now, but he had a lot of girlfriends. Let's just put it that way. And one of the girlfriends was actually a nuclear physicist.
Wow.
And she had a job working at the Pickering nuclear power plant.
Wow.
And so we had this real life example of a woman who had a PhD in physics and had a job, a really good job, a stable, secure job. I don't know, like I wasn't in on any of the financials, but I think that really helped change his mind because he saw an example of like a real physicist, a woman physicist. And I think that helped a lot actually. So it was partly me just deciding to do it. It's tough though. People don't like to go against their parents. Not just if your parents are financially supporting you. I don't know what it's like now, but I lived at home. I had a scholarship from the government, from the national government for about $2,000 a year. And that was the cost of tuition.
Oh.
Yep. And I had my summer job, which was for about $4,000. So I can't say I was like fully financially independent, but living at home, tuition covered. It wasn't like I was beholden, I didn't feel like it's just a little bit of a fine line, right? Because your parents support you in many ways. So I think it's hard to go against your parents.
So when exactly did you decide like to scrap the whole pre-med idea and go into astronomy?
It was probably after my first year. It was
After
probably
your
pretty
first
quick,
year?
actually, yeah.
Okay.
So you
Also-
went through the pre-med and you're like, no.
I actually didn't do the pre-med. What I did in my first year, which was also a really bad idea, so I hope everyone's listening. But a lot of us, we grow up thinking harder is better. So I took all the sciences and math in my first year, and all but biology, I did like the hardest course available.
Ouch.
And so I kept all my options open. So I didn't do pre-med per se, but I made sure I didn't rule it out. So it was really hard. I don't recommend it. Right now, actually I have a son in college right now. We call it college here, not university in the States.
Yeah.
I learned from one of my undergrad students to only take one really hard class a semester, if you can. So like if you're taking quantum mechanics for the first time like ever in your life, then you should take some easier classes, like maybe an elective that's really easy, or take a math class that's fairly standard and not like, so, once in a while there's like a known to be really hard math class. And that's really just to keep your own sanity, really, because there's a crunch time and it's hard to keep all the balls in the air and it's hard to like retain, right? I don't know. You don't look convinced.
No, I think we're very, very convinced because we have done almost opposite of what you just stated.
Oh, good. I'm glad.
Yeah,
That's what I recommend.
No. So yeah, we definitely have been flustered in a few semesters because of like the variety of courses, but we do try to keep it a little light and a little heavy. This semester, unfortunately, I kind of decided, why not, completely make my life a living hell with 6 courses, all core courses. So that's what I'm doing, just to see if I can handle it. Trying to push my limit. So that was kind of my thing. And in university, when you went through astronomy courses, like I'm assuming you also you specialized in a lot of physics courses as well, right?
Yes,
So,
in fact, I actually didn't take astronomy. I don't even think I took a single astronomy class. I decided to do math and physics. And I did it because, you need, I don't know. I did it in the spirit of harder is better. It's too late to change that. And I did the math and physics specialist. So I did like the pure math, and it was really hard. And I just want to I can say like a lot of it, I don't feel like I understood it. Like my first year math class, everyone failed the first test.
it's probably 157. Probably MAT.
They probably changed the course code.
Yeah,
but
that's the course code.
It's like proofs. And the problem is that they never taught us how to do proofs. Here in my kids' public high school, they do proofs actually.
What?
Yeah. So but we had never seen proofs. We had no idea how to do them. And the textbook didn't really explain stuff. So it was really tough. And so everyone failed the first test. And the second test, I got a 90.
Oh.
But the second test, you know what it was? The second test was the entire first test plus one extra question.
Oh.
Okay, so I didn't get the extra question, but and you know what? Most of the class still failed because they didn't think the first test would be repeated because we had moved on to new material.
Wow.
So anyway, so I did that, and I should have just done regular math because it's more applied, which is what we need in physics. But I did have I remember a class in like 3rd or 4th year on differential geometry, and I really liked that class. I don't remember a lot of the details, but I'm guessing since I'm probably the same age or older than my professors were, they're probably not around anymore. But I remember my professor, his name was Professor Sen, and I really liked something about him. I'm not sure. He was a good teacher. And if I remember properly, we only had one homework set due in the middle of term and one homework set due at the end of term.
Oh.
But it took like 100 pages of writing, to complete it. But it wasn't impossible. It was like somehow, maybe I hesitate to say joyful, but it was really it was just, it was enjoyable. So that's the one class that I don't remember all the details, but it has like a good feeling when I think about it. So I did math and physics, and I don't know if I should be telling you the next part of this story, but I really didn't like my electives.
I think
I think
we can agree.
Mutual feeling.
I think it's mutual.
Yeah, I don't know if I should tell this to you. So I was like, okay, I kind of left some of them to the last minute. And with my sister's encouragement, I wrote a letter to the people who decide if you can get a waiver and not take some of them. And I had a really good argument. You're not going to be able to copy my argument though.
Yeah, what is this argument? I'm so curious now.
Because at the time, the math and physics specialist program, it like had a lot of required courses. You know, if you take like almost like a double major, there's not a lot of room left.
Yeah.
And at that point, I was planning to go on to grad school. And I said, look, I can take these electives or I can take more math and physics classes, which will do me better for my education in the future. But the part you're not going to be able to, this is why you can't do it, is because I also said, since the program's changing, I'm the last year with so many requirements, because the following year, there was going to be like a permanent change to fewer requirements.
Oh.
Yeah, I said, you won't be setting a precedent.
Okay.
So no one can come after me and ask for the waiver, because they'll have more room in their schedule to take the harder class, you know, the specialized math and physics classes, because they won't be required to take so many core courses. I don't know. And so, yeah, I got out of taking maybe a couple of those electives, which was good.
Wow.
I should there's the one school of thought that you're going to university for like a broad education, right? And we want you to come out a better writer and better at thinking about the world around you. But some of us, let's just admit it, it's a struggle for us, you know? I mean, we're not, I know some people will disagree with this, but, you know, we're not forcing other people to take physics, for example. So I have two sons. One of them is 16, one's 18, one's already in college, and he goes to a technical school. It's kind of like the University of Waterloo. It's called Worcester Polytechnic Institute. And it's like a hands-on, mostly an engineering school, but they have very few requirements. Okay, like electives. I mean, not requirements, very few like elective requirements.
Okay.
On the other hand, my younger son, he's very good with writing, so good with like any kind of debate or arguments. Like, so for him, I would support him getting like a broader education because it's something that resonates. So I don't know how it is today, or if people try to embrace those electives, or if they're like, let's just kind of try to get them out of the way.
Right. Well, when we were in our first year, I don't know how it was before, but in our first year, we only had two requirements, which was math and physics, and that's it. Everything else was just electives. So I ended up taking like a course in like classics, an English course, and like some geography courses and all that stuff. But I actually, like, same thing with you, I preferred just taking the math and physics courses instead of going, although it was interesting, I preferred doing the other stuff. And then also, for our math course, we had a similar experience to you. On our first midterm, we had to do a bunch of proofs and everything. We've never done proofs before. And well, we didn't fail, but we were pretty close to failing. And it was a real like reality check, because you go from high school to like doing multiplication and stuff. And then here where you're trying to do like mathematical sentences and prove things.
Structure and stuff. Yeah. It's very different, but I think that helps you. I want to know your opinion though, because you've actually done like the significant proof route. I want to know because in my opinion, like, even though yes, it's not very applicable for physics, it still gets your mind thinking in a certain way, right? That I don't think can be achieved just with practical physics. Or am I wrong? What do you think?
I think I would agree.
Yeah.
Yeah. I would still rather have not done it, but I think I do agree.
Because I think just like the way of thinking that some of those courses kind of instills in you is very, very, very powerful. Because I remember just, mundane everyday tasks and or something that we're doing, and I always think, oh, where's the proof of it? Or like, oh, how do I show this? Or like something like that. And obviously I'm not saying like tasks that I'm performing, I'm saying anything relating to school, of course. So it's always like, I just think that I'm looking at an equation right now in astronomy, and I'm like, oh, like, how does that really make sense? Versus if, let's say, haven't taken this course, I would have maybe just been like, okay, that's a formula with a bunch of variables.
Right.
I think that's a powerful thing that might also instill,
Makes sense. Yeah.
So yeah, I think we can move on to maybe talk about your graduate experience.
Sure.
So yeah, what happened after you graduated?
Well, after I graduated from the University of Toronto, I went to Harvard University, and I went to study astronomy there.
Was it direct? Like, do you like next year, or did you take a few years?
I went directly, actually.
Direct. Okay. Okay.
But I'll just say one thing, because I really hate standardized tests, and I had to take the GRE, and that now it's not required in a lot of places, but I totally bombed the GRE. Like, I didn't study. I had like a boyfriend, and like we went out the night before. So instead of, really preparing I was like, I'll just see what happens. So I took it and I just realized I should have prepared because there were like giant sections that I just wasn't familiar with. And you're not supposed to guess on exams like that because you get negative points if you get it wrong. But I just guessed anyway, and I just totally bombed it. So I thought that the US wouldn't be for me because I did so badly. But in the end, they overlooked that. So I went to Harvard, and it's a great place there because it's on the same property as the Smithsonian Center for Astrophysics. So it's called the Harvard Smithsonian Center for Astrophysics. And so there's so many researchers. I don't even know how many, maybe like a couple hundred, I don't know, there's a lot. So there's a lot of activity there, and almost every part of astronomy seems to be represented there. And Harvard, of course, you have this image of it being very wealthy, and it is. And for research, that's a really great thing because it translates in being able to work on new things where the professor or professors, their department might not have funding. Because oftentimes we have to write grants and then we hire students, but the student has to work very closely aligned with the grant because that's what the sponsor is paying for. Mm-hmm. So I got to the university, I worked in cosmology, and about 1 year after I started, an amazing thing happened. The first report of an exoplanet orbiting a sun-like star was announced.
Wow.
And this is the planet 51 Peg B. Now, this is a pretty interesting planet because people searching for planets were expecting to find our solar system repeated elsewhere. And it's easier to find massive planets. So Jupiter is what everyone was looking for. But our Jupiter, it's 5 times the Earth-Sun distance. It takes 12 years to go around our sun. This new planet was about Jupiter mass, but it only took 4 days to go around its sun. So something like 100 times closer to its star than Jupiter is to our sun. And we know from observing stars forming, there's not enough material that close to the star to form a Jupiter mass object. So people didn't really believe it. There's like a huge amount of pushback, but nonetheless, the summer after that was in the fall of, I want to say that was the fall of 1995. So the summer after that, I had finished my cosmology project and it was time to choose a PhD. And my research advisor said, why don't you work on these new planets? A few more had been discovered. And, by Kepler's third law, a planet orbiting very close to its star is a planet with a very short period orbit is also very close to its star. Actually, I kind of mentioned that already. And so the task he assigned me was trying to understand the atmospheres of these so-called hot Jupiters, right up close to the star. How different would this look from Jupiter? And that's started my entire career path.
Mm-hmm. So I'm guessing you really have to get lucky with these kinds of alignments, right? Because if you're looking at a star in the distance, there could be like a very interesting case out there, except it's like normal to your plane of view, and so it doesn't actually cross the path of the star, and you'll just never find it.
Well, that is correct. And today, the method you're describing called transits, when the planet goes in front of the star as seen from our telescopes, that's the main way we find planets today. But there are about 5 or 6 mainstream techniques. And at the time, it wasn't transits that were in vogue or like were working. It's a method called radial velocity. And that is astronomers measure the line of sight motion of the star by the Doppler shift. And the concept is that the planet and star, they're actually orbiting the common center of mass. Mm-hmm. Mm-hmm. Sometimes that's inside the star, actually. And so the star wobbles, and astronomers can measure the line of sight of that. And that's how they discovered the planet. But we don't see the planet, only like this line of sight Doppler shift. And so there were a lot of reasons people tried to argue away that it wasn't a planet, but it was some new kind of stellar pulsation or something else. Mm-hmm.
So
but it's still a really hard problem.
Yeah, so in this radial velocity method, can it not also be impacted by other surrounding planets? So you're maybe not determining the correct one, or like I'm just thinking there can be a lot more uncertainty or just more, error with this method because you're just looking at the star versus in the transit method, you're actually looking at, oh, this is a dip. Okay, that's a planet.
Right. Well, the same thing can happen with transits, actually, but not as easily, as you point out. But for radial velocity, usually there's one planet whose signal dominates. And so you see that planet, and then you remove that signal from the data. And then you look and see, is there anything else? And you kind of keep doing that. And then you can make a joint fit to all the data. You can put all the planets, back in the data, so to speak, and then do a joint fit. So like, that's not my pure specialty, but nothing comes to mind where, actually, no, you can just get more data and get better data. So yes, things can always be confused, and they usually sort themselves out.
But would you not need to know the properties of the planets because how would you like take them out of the system? Because let's just say there's a star-like system or sun-like system 5 light years away with like 5 planets, and let's say we are interested in the third one that happens to be in the Goldilocks zone by our estimations. Now we don't know any properties about these planets, right? So how would we be like factoring in and factoring out? I'm just interested in knowing how we're really determining it via this radial velocity method, because it's an interesting method.
I'm not sure if you've come across, I think you said you're taking statistics.
Yes.
Have you come across like a periodogram, like looking at something in frequency space rather than time space?
I have not. Maybe you could explain.
Well, okay, so just think about, let me think about how to explain this for a second. Let's imagine you have a data set that's a function of time. So it's radial velocity or transits or anything really. And you're just sort of measuring data. And you want to know, is there recurring phenomena that happens either every minute or every 5 minutes or 10 minutes or 15? You can actually make a plot that instead of being like, 1 day, 2 days, 3 days, 4 days, it's actually in frequency. So instead it asks, is there a signal at 1 day, 2 day, 3 day, 4 day? It's just like a mathematical tool to see if there's a periodic signal.
Right. So just taking like a Fourier transform of like a data set.
Yeah.
Okay.
So imagine that you found a Jupiter and it's a huge signal. You can fit the data and like subtract it out basically. And then you can do this Fourier transform and then try to see, is there another periodic signal in the data? But if your data is not good enough or the signal's too small, it won't show up actually. So you can't necessarily like keep doing this and finding more planets.
Right, because I'm guessing like an Earth-sized planet doesn't really affect the common center of gravity between the sun and the Earth is so negligible from the center of the sun that you wouldn't really be able to tell if you were looking at a solar system in the distance. These small planets wouldn't cause like a noticeable wobble in the star.
Well, people are trying actually. It doesn't yet cause a noticeable wobble, but people are pushing for that. So let's just take some numbers for a minute. So this first planet, 51 Peg B, around a sun-like star, its peak radial velocity signal was 400 meters per second. Okay, so maybe you want to think about that in terms of running, okay? 400
Very
meters
fast.
is pretty far.
Very
so you're not
fast.
going to run 400 meters per second, most likely. Our Jupiter signal, like if a Jupiter analog, would be about 12 meters per second. I don't know if you can run that, right? That's
still pretty
Right.
fast. I mean, Usain
fast.
Bolt was 10, like 10, 11. But yeah.
Okay, cool.
Yeah.
So now an Earth would cause a signal of about 10 centimeters per second.
Oh.
And that's easy, right? I think everyone can. I mean, it's like one step is way more than 10 centimeters, right? For you, like young, healthy people, one step is quite a lot. So that's just to give you some numbers. So it's very hard. And one of the main challenges, by the way, the Canadians have a big role in this, in having helped make more precise radial velocity measurements, because when you're measuring the Doppler shift, you need a reference frame. I mean, a lot of physics, right? You learn about reference frames. And people used to use our sky, the like signatures from spectra on our sky, like molecules in our atmosphere causing a spectrum. But the Canadians, Gordon Walker, he's retired from the University of British Columbia and lives in Victoria now. And what they did was they said, we're going to make our frame of reference more solid, like more controlled. And they made a gas cell of hydrogen fluoride. And what they did was the light from the star went through their telescope and passed through the gas cell, where it got an imprint of like almost like a ruler-like set of lines from the spectrum from hydrogen fluoride. And so they were able to improve this radial velocity by like something like an order of magnitude or more in precision. Like anything you can do 10 or more times better is like phenomenal. So they figured that out, and other people did other things and made that better. And like in later generations, people would take the instrument and put it like in a vacuum Like, so it's stabilized from air currents.
Mm.
And later people like used a fiber instead of a slit to get the starlight so they could control how much light made it. Like there's many, many improvements brought it down. And now we're kind of at the level where the star itself has contributions to the signal. Star spots and other phenomena on the star are often larger than 10 centimeters per second.
Oh,
so it's
wow.
not clear where this is going, but there are dedicated telescopes and methods to try to be able to reach that level to find another Earth around a few choice, bright, quiet stars.
Because I know with like severely varying stars, we're actually doing a lab. Interestingly enough, in our astronomy class, where we have a practical astronomy class, and we are actually determining exoplanets via transit method. So that's really
Nice.
cool. And in this method, we're also learning about, how much these stars simply just pulsate, just variable and Cepheid stars, and the fact that, some of them just regularly have a large, difference in flux and just a difference in radius. They can pulsate in and out. So I'm assuming all of these factors obviously just make the measurement that much harder.
Sometimes, like a Cepheid, they're typically really big stars. They're evolved stars, and they're probably too big for us to find a planet around. But remember, these transits last a few hours, and they have a very distinctive shape. So if your Cepheid has a period of like a day or days, that probably actually won't interfere.
I guess that's right.
Yeah, but there's other types of variable stars that would, like spotted stars that are rotating at a certain, period. And there's other just random things that make them variable. But hey, that's pretty awesome that you do transits or variable stars for your exercise in your class. By the way, that's what I studied when I was the summer intern.
Oh.
We had a program, my professor, Don Fernie, had a program monitoring variable stars like over many years. So I had a list of stars that he would assign to me that I would rotate through during a night.
Oh, wow.
And these were like Cepheid variable stars?
Some of them were, not all of them.
Okay.
They were all sorts of variables. But I'm not sure if you know that our North Star, Polaris, is a Cepheid.
Oh, I didn't know that.
I did not know
I
this.
didn't know that.
I did not know this. So what is the because I think we've learned like the importance of it in our night sky and like how to determine it and how to determine that, okay, this is most probably a Cepheid or it's like a variable star. But what is the I mean, I don't want to say purpose because I guess there's not a lot of purpose to a lot of these things, but what is the significance of like a Cepheid star or, as you said, a spot star, something that I haven't heard of before, or any of these wilder stars that sometimes you might come across while looking for these planets?
Like sometimes, I think like you said, there's often not a reason. We just try to study things, find things, classify, try to understand how stars evolve, how they change with time. Cepheids, you might have learned, are often used as standard candles because their period corresponds to their absolute brightness. So people use Cepheids to understand like, distances in our galaxy and beyond.
So they can be very useful then in that regard as well.
Some stars can be very useful.
Interesting.
So yeah, so that was the topic that you decided to go with for your PhD.
Exoplanets, atmospheres of exoplanets. That's
Atmospheres of exoplanets. So what is it that you found out on your journey of writing your PhD?
What did I find out about the exoplanets?
Yeah, like what did you discover? What did you write about?
Well, my job was to figure out what their spectra would look like because, a lot of astronomy is about visible or near infrared spectra of objects, stars and galaxies and other things. So the thing with these hot Jupiters is they're so close to the star that they're being bombarded by radiation from the star. And I had to figure out what temperature would the planet atmosphere be, as a function of altitude, and what would the chemistry be there? What molecules would exist and what would the planet look like? So I found that the planets would have water vapor in the atmosphere. In our planet Jupiter, water is locked away into ice clouds. And I found out we could have carbon monoxide would be the dominant form of carbon. I also found out, this might just sound really obscure, but the alkali metals like sodium and potassium would be in atomic form, which is sort of interesting because planets are usually, even the hot Jupiters, they're usually cold enough that almost every atom wants to be in a molecule. You know how like super hot things are like a plasma or ions?
Right.
And then kind of cooler things are atoms. Cooler things still would be molecules. And if you got colder and colder, instead of gas, you'd have a liquid or solid even.
Mm-hmm.
So kind of in that whole scale, I don't know, I wasn't expecting a hot Jupiter to have atoms. They should have molecules, I thought.
Mm-hmm.
So those are I kind of learned that, and I learned the temperature of these planets. And I did some other work as well, trying to understand these planets in reflected and polarized light to see what we could learn about them.
Mm.
I know that sounds super exciting.
Yeah. What did you learn about them through that light?
Well, I think the biggest thing I learned was that, well, let me think for a second. I mean, what I learned about them is they're very different from Jupiter. If you just want like one bite-sized piece of info, very different.
Very
like
different.
Jupiter has a lot of ice clouds. It's very bright. You know, Jupiter has a lot of banded structure. What I learned from my computer simulations was that these planets could possibly be very dark. I learned, you know, they could have clouds, not of water, but of things like, believe it or not, iron, liquid iron, little like rock particles in the sky. So iron, aluminum oxide, like magnesium. So yeah, I learned they could have clouds, but the clouds would be very different from what we have on Earth. I learned that the dominant molecules and atoms in the atmosphere, because it's so hot, are very different from Jupiter.
But with these planets so close to the star, how did they even have an atmosphere? Like, wouldn't it just be completely vaporized, I would assuming, with the fact that it's so close to the star?
Yeah, that's actually a question I got asked quite a lot. And the answer is they can still have an atmosphere because a planet that's, you know, Jupiter mass is actually quite massive. And its gravity well, if you will, is quite deep. And so it can hold on to its gases. However, later on, when I was doing my PhD, lots of planets have been found. And people are thinking a lot of these exoplanets close to the star that are much less massive than Jupiter, people are thinking that they might have lost their atmospheres and like a whole lot of their material from being so close to the star. And there's been even evidence, some people have observed with Hubble and other telescopes, like hydrogen and helium leaking off the planet.
Oh.
So it's not really clear exactly. So the answer to your question initially is like, it's fine, the planet's pretty massive. But a sort of, you know, more nuanced answer is it looks like a lot of planets are losing some atmosphere, and in the past might have lost a lot of their atmosphere. And there's one exoplanet in particular. It's a small rocky planet very close to its star. There's evidence that that planet has no atmosphere. But that's a small rocky planet, and it can't really hold on to much.
So the main case is, well, gravity. Main case is the size, I should say. The mass of the planet.
Mass
of
and
the
size,
planet
I
is
would say.
mainly.
And so is it more common in the universe to find hot Jupiters versus cold Jupiters, or is it just that we don't really have the tools to detect cold Jupiters more frequently than hot Jupiters?
It's the second thing, what you said. So hot Jupiters aren't that common, but they cause a big effect on their star. And so a lot of them have been found. We're not sure yet how common cold Jupiters are. If you're using radial velocity, remember it takes 12 years for our Jupiter to go around our sun. And there haven't really been too many 12-year periods since radial velocity method was precise enough to find Jupiters, if that makes sense.
Yeah, that's very true.
So we're not 100% sure how common Jupiters are. I think the evidence is leaning to say they're not that common, but there's certainly, but the hot Jupiters are rare. They're just easy to find.
So you also said that, well, we discussed like two of these methods to detect exoplanets. What were the other methods that we know of right now?
Well, one method we call direct imaging, where we block out the starlight to see the planet directly.
How?
And right now, we can do that we can block out the starlight and we can find planets very, very, very far from the star. And the planets we find, they're much younger typically than our solar system, because big giant planets, you know, when they form, they have energy trapped on the inside from, for example, gravitational potential energy from when they collapsed, you know, gets stored as like heat energy, and it takes a long time for it to leak out. So when a planet is really young, a massive planet, it has a lot of, it's giving off a lot of radiation as that heat initially leaks out. And then also more massive objects are hotter as well. So we can find massive hot planets, massive young hot planets far from the star.
Sorry, so how do you block this light though?
Well, there's a device called a coronagraph. And a coronagraph goes inside the telescope and it blocks out the light from the star. It's actually quite complicated. You have to have more than one kind of optical element inside your telescope to do this. But yeah, it comes from the 1920s when a French optical physicist, Leo, wanted to observe our sun during a solar eclipse.
Oh.
Have you ever, I'm sure you've seen pictures of solar eclipses, right?
Yeah.
Oh, yes.
And you know how you can see the corona? Like the kind of white plasma coming off. Well, he wanted to be able to see that on any day, not just when there's a solar eclipse that you have to travel really far to.
Wait, but isn't that just the UV filter? Isn't that just the UV filter? Oh, because like usually when we looked at the sun with a telescope, we just put a UV filter or like a specific type of filter. But you're saying to block out. Interesting. So he invented this thing that blocks out the light of the star.
Yeah, because when you have a filter, you're probably seeing little prominences, like little loops coming off the sun, maybe.
I don't recall. This was a long time ago, but I could, sure.
Well, after this, for everyone listening and for you too for afterwards, you have to Google solar corona. It's something different. It's not bright enough to see with the UV filter. You have to literally block out the light from our sun so you can see this hot plasma that's really like, spreads way out. So he figured out a way to block out the sunlight so he could see the corona, and hence it's called a coronagraph, actually. And it's a device you put inside the telescope and block out starlight.
That's very interesting. That's actually, I'm actually looking up pictures right now, and I definitely understand what you're saying. Yeah, definitely worth searching up the solar corona just to get a better idea of this.
So there's a really famous planetary system called HR 8799. And it was actually discovered in 2008 by Christian Marois, who's an astronomer who works at in Victoria, British Columbia. And it's a pretty amazing system. You can add that to your list of things to look up. But there's 4 planets, 4 of these, hot giant young planets orbiting that star. And when they've observed it with a variety of large ground-based telescopes, they've even seen them move along their orbits.
Oh.
Yeah, so that's direct
that's
imaging. And we're trying to push direct, everyone's trying to make direct imaging better and better. But in order to find solar system like planets, we think we have to go to space, send a special space telescope up there to be able to block out the starlight to see the planets directly.
So as of right now, the only method that we're using is ground-based telescopes.
Well,
isn't Hubble, if I'm not mistaken, sorry, but isn't Hubble also an exoplanetary detector?
Let me just say it this way. One of my colleagues explained that pretty much every telescope, should have an instrument with a coronagraph, and even Hubble does.
Okay.
But how good it is another story. Okay. So Hubble has a coronagraph, and it can, Hubble has a coronagraph, but it's not really well designed for this. I don't know if you've learned in astronomy about lambda over D. I don't know if that rings a bell, but to spatially separate something. Yeah, okay, you have, great. So maybe, so to spatially separate something, what matters is the wavelength you're observing and the diameter of your telescope. So think about Hubble for a moment. It's 2.4 meter mirror diameter. Now think of a ground-based telescope that has a 10 meter diameter or an 8 meter diameter. It just buys you so much more in separation, and you have to separate the objects and block out the light of the star. So you just win a lot more on the ground by having that big diameter.
Right. And I actually remember this was last year, our very first astronomy course, and our very first problem set in that course. We did do like lambda over D for telescopes because we were doing comparisons between like telescopes and also our eye. So we'd use like the diameter of our pupil and like the optical wavelength of like to see how well we can like see like the resolution if we were to look with the naked eye. So that's pretty interesting.
Also, the biggest problem right now, also with the space thing, is just the fact that we can't really repair them very easily, right? like James Webb, for example, I'm pretty sure it's just there now. I don't think we're touching it anymore.
Right.
So like, for example, so
No,
I
we're
guess
not,
that's
yeah.
also a very big thing. But is there any upcoming mission that's going to help in an exoplanetary detection for space, or are we still content with where we are?
Oh, we're never content, right?
Oh, I guess I shouldn't have said content, but
No, I know.
Yeah.
Well, we did have really big plans. My favorite project of all is called Starshade. Starshade is like an external coronagraph outside the telescope.
Oh,
And Starshade is a giant specially shaped screen that would be tens of meters in diameter. And it would formation fly tens of thousands of kilometers from a space telescope. And that starshade would block out the starlight so we could see any planets around it.
Wait, did you say
So we have
tens
the
of thousands of kilometers?
Yeah, tens of thousands of kilometers.
Oh
And the
my God.
reason why, I mean, you might ask, why can't I put a starshade like right up close to the telescope? And the reason ends up being diffracted light. Because by the way, the coronagraph, or a giant screen in the sky, it actually ideally can't be a pure circle. Like this giant screen can't be a circle. Because if you have a big circular screen blocking out a point source, what happens? You
What about
actually
the edges. Is that what you're
yeah,
talking
you
about?
end
Like
up
the
seeing
edges
rings.
the edges would all diffract.
Yep. Because light can act like a wave, and the light can bend around the edges of a giant circular screen, creating a ripple pattern. So most people see this at some point in physics. It's crazy. Like blocking out a point source, you don't block it out. You end up getting rings. And these rings of light, concentric rings, they're actually brighter than the planets you'd be looking for.
Oh. Wow.
Yeah.
That just makes it so much harder.
So what people figured out mathematically was that you can have a different shape. So instead of a giant circular screen, imagine having like a giant, it's shaped like a sunflower, like a screen with like big petals. And what this does mathematically and in real life, it actually would let the starlight interact with itself and cancel itself out.
Oh, so
the
like in
analogy
each
I
of
like
the petals, it would cancel itself out, is what you're saying.
The light
I
interacts
understand
with
that.
itself. So it diffracts
Yeah.
around the edges
Yeah.
in a special way. There's an analogy I really like. It's like, which most people can understand better, but it's like throwing a pebble in a pond. You see ripples. Well, imagine throwing a pebble in the pond, and instead, the pond is perfectly smooth. I mean, that would be just really freaky. But if
That
the
would be
pond's
very
perfectly smooth, yeah, and all the waves are pushed to the outer edges. And that's ends up being what the starshade does. It makes it perfectly dark. But then there's some regions where now it's like quite bright, actually.
But obviously, it's like completely impractical, right? It's just a theory. Like it's just
No. The starshade is practical. In fact,
What?
it
Tens
has
of thousands.
heritage.
How?
Yeah.
How is this practical?
Well, first of all, let's talk about the size first. So,
Okay.
and you're gonna have a lot of things to look up after this talk, but
yeah, no, I'm
Starshade.
making a note of all of this to put down in the description.
yeah.
So don't worry.
So, what's really interesting is people first thought of Starshade in the 1960s, and it's been revisited every decade since until now. A lot of work has gone into it, and it has heritage from large radio deployables. You know, people have sent up things that fold and then deploy. So we have that going for us. Now, formation flying, okay, true, we've never flown something that far away, but you have to think of it more as a control problem. So can the telescope send a signal to the starshade, you know, to make sure that they're lined up properly? Think about it.
Right.
So the problem, what it boils down to is this. The starshade would have a laser on it shining towards the telescope. You know how light spreads out? So the telescope would have to have a detector that could not only detect that laser, but send information back to the starshade to make sure it's lined up properly. And in fact, people have worked out this in incredible detail. First, the starshade would have a LED bank. It's sort of funny, right? Like a bunch of lights. So the starshade could see, so the telescope could see approximately where the starshade is as they're getting to line up with each other. And since both would be able to communicate with the ground, we'd know approximately where they are anyway. So then as they start lining up, the starshade would have a laser, you know, that would go back to the telescope, and the telescope would have a receiving element, like a special guide camera to see where it is. And it would send a signal back to, like, you know, close the control loop so it can get into place. Now, the telescope would know when the starshade was exactly in place, because at red wavelengths that we would let some light actually leak around, and the telescope would be able to spot a red light leakage, the airy ring pattern that you don't really want, and that'll know when it's locked into place. So it sounds really far-fetched for sure. I mean, it is pretty crazy, but there's a lot of crazy things that engineers have figured out how to do. And I want to assure you, if you dig into this, you'll see that it's viable.
Wow. That's actually very cool. So this is one of the penultimate ways. So there is there a final way of detecting? I guess this is one way, so to block out the sun or block out the light, but is there another way of detecting these planets?
Well, there's a couple other ways that I'll get to in a second, but I just want you to know that, we talked about how trying to find another Earth at like the 10 centimeters per second, like that's really hard. And the starshade is really hard, but every way we have to find an Earth is hard, pretty much. So I just kind of wanted to say that.
Yeah, no.
So we can move on to the last two techniques, which I think I'll just describe briefly. But one of the methods, it's called astrometry. And remember we talked about the line of sight motion?
Yeah.
Astrometry is like the 2D motion on the plane of the sky. So, the stars actually, as the planet and star orbit the common center of mass, the star is actually wobbling in like 3 dimensions. And so one of the dimensions is the Doppler shift along the line of sight, but then there's the other 2 dimensions in the plane of the sky, actually. And astrometry is like the precise measurement of positions of stars on the sky. And you'd technically be able to see a star wobble with astrometry, but it's very, very hard to do.
Right.
And no planets have been discovered that way, although some have been followed up with astrometry.
Yeah, I could see how this would require especially precise tools. As the distance you're trying to measure these stars increases, the shift on your I want to say like CCD screen or like any kind of detector will become less and less noticeable. And so definitely like a very specific case by case basis where, we can actually see this wobble in 2 dimensions. And so therefore we can infer planets. Yeah.
Okay. So the last method I'll tell you about, this will blow your mind. And this is one to keep track of, because later this decade, a space telescope will be launched. And one of its main programs is about this method called gravitational microlensing.
Definitely
so
heard of it.
I want you to imagine, so out there in outer space, right, there are stars and planets just kind of floating around that we can't see at all. But if these stars and planets, if they line up perfectly with a very, very distant background star, believe it or not, they can gravitationally lens the background star. Because Einstein told us that mass bends space. And so every star and planet, like they're kind of bending a bit of space around them. And so you have to think of it like the very far background star, some of the light rays bend around that planet star system, just like a lens. Like it's kind of hard to explain without visuals, but the star, the intermediate unseen lens star, it literally acts like a magnifying glass. And depending on how well it's aligned with the background star brightens. So let's imagine for a moment, there's a fixed background star at the center of our galaxy, towards the center of our galaxy. And right in between, just imagine there's a planetary system kind of slowly moving by. What we'll see is the star brighten with time. It can brighten like almost, 50%. It can brighten a few times. High magnification events, it can brighten like 10 times. And that star kind of brightens on a graph. And then eventually, when the object finishes moving along your line of sight, the thing goes back down. And believe it or not, astronomers can monitor, it's called the galactic bulge, but they monitor like millions and millions of stars. I don't know, maybe it's 10 million or more. And they analyze the brightness of these. And if the brightness and they have like hundreds, maybe, I don't know, hundreds and hundreds of events going on at any one time. And if the brightening starts to deviate from like a very nice smooth curve, that might mean there's a planet. Because imagine like a spherical mass object moving by, everything's really nice. But all of a sudden, there's a planet there. There's like a little weird blip. So what happens is if you're part of the microlensing team, one of the teams, and one of the light curves starts to deviate, you'll get like a text message. And it would be your job or all the people getting it to figure out which follow-up telescope can now hammer away and like be observing that thing nonstop, because the star signal can last like tens of days or 100 days. So it's very gradual. But the planet signal might only last 20 minutes. As soon as you see something changing, you want to monitor it. And it's quite an exciting, very mathematically kind of intricate field to get from, the weird light curves back to what kind of planets might be there.
Yeah, because we actually have
so
to back analyze it, right?
You've got to back analyze it.
Exactly.
Now, one of the sort of unfortunate things about this is once that planet and star have gone by, do you think you can ever see that, unseen dark lens star and planet again?
Probably not, right?
Probably not. So you sort of have one shot to kind of figure out what's going on. And after that, it's kind of more of a statistical kind of discovery space. So the great news is there's a new space telescope called the Nancy Grace Roman Space Telescope. It's supposed to launch later this decade. And one of its main programs is microlensing. And it's going to find so many planets. And microlensing is really special because remember before we were saying how hot Jupiters are rare but easy to find?
Yeah.
Well, microlensing, it can't find hot Jupiters, but it can find planets between about it finds planets like, further out, like it's sensitive around 1 to 4 or 1 to 5 astronomical units. And it can, if the better things are aligned, the higher the magnification. And so if it looks at enough stars and picks up some high magnification events, it can actually get down to Earth mass planets and smaller.
So for this like light curve graph, would it be the case where as the stars start to align, the light curve goes up, and then if the planet comes and interferes, there would be kind of like a very small dip in the light curve? And then there'll
be another rise.
Because
remember, these are acting as magnifying glasses. There'll be another rise. And the conceptual way you're supposed to think about it is the unseen star and planet lens, they're bending space. And so some light rays that would normally go away from you, they're actually getting bent towards you now.
Okay.
It's a very complicated, not necessarily easily understood method, but it actually works and it delivers planets.
Wow, that's amazing.
Oh, that's very interesting because I'm actually currently doing an experiments course in my physics class, and a lot of times the way that my professor will give me the reports is sometimes he'll give me the theory with the theory being wrong, so that when I do the experiment, I have to figure out that the theory was wrong. So where that statement is basically leading into a question is, in the very first moments of, like at Harvard when you were seeing these exoplanets to all the way now, did you ever discover something that, didn't really bode well with theory? Because that one thing that I'm remembering now that you mentioned, Jupiter, it had atoms, but my understanding, it should have had molecules, like something like that.
Jupiter.
Like the hot Jupiter. So something like that, when it like breaks your understanding of theory, what is that doing? Is that changing what we're understanding about the theoretical world? Or is that just, my measurement was wrong, or something in my measurement was wrong?
Right. Like in this case, it was neither really, because that was just my own paradigm inside my head.
Okay.
But it didn't break any theories because, as soon as I'm just saying, I expected something. But I could have, if I'd worked out the theory, I would have realized my expectation was wrong.
Okay.
But I used my computer as my experiment to show that my own thinking was wrong. But that particular thing didn't break any laws.
Okay.
I might have had some minor brushes with things like that, but my own work has not encountered something that I can think of that was totally wrong. It's more challenging people's perceptions, I'd say.
So usually when something is wrong, it's like, okay, something's wrong with a measurement tool, or like I've made a mistake here.
I mean, it takes a really long time for things to be found to be wrong. Like one of my main mentors, John Bacall, he's not alive now, but he studied neutrinos coming from the sun. Do you know about the Sudbury Neutrino Observatory?
Yes,
in
actually,
Sudbury, Ontario?
yes.
Believe it or not, my husband got to go on a tour. and you go down like 2 kilometers. It's a working mine.
Oh, that's so
and then
cool.
you have to go like along this path, and they show you these like safety rooms, like in case something goes wrong in the mine and part of it collapses, you've got to go in the safety room. And then when you get to the neutrino observatory, you have to take a shower and like put on a special suit around your clothes so that you don't like put any dust or anything into the mine area, into the neutrino area. But anyway, so these neutrinos are unseen objects, and like 1 billion of them, go through your thumbnail at any moment. And my mentor, John Bacall, he had worked on this for decades, trying to perfect the calculations and get measurements made of the processes happening in our sun that give rise to neutrinos. But he came up like maybe wrong, if you will, every time, because his predictions didn't match like the amount of neutrinos coming. And so I'm really glad he got to live long enough, because people discovered that the neutrinos coming from our sun, they change type before they get to Earth.
Mm-hmm.
And so there's a lot less of one type of neutrino than you expected, because even if that's your calculation says, I have this many neutrinos of this type leaving our sun, and then at Earth, you don't measure that, you measure something else. Like, what are the chances that you're right and physics is wrong?
Right, exactly.
I mean, that there's new physics there. Or what is the chance that you just made a mistake? Like in his case, he was actually correct. His calculation of what's leaving our sun is correct. No one thought that neutrinos could change their type on the way here. That's incredibly rare that you do, and someone does an experiment to match the data, and it turns out there's new physics. Like, that is just, it's got to be one of the most amazing things ever, like here on our planet.
Wait, so
But in my work,
sorry, yeah.
But my personal work, like, it doesn't challenge things that way. Like, probably in exoplanets, we're not going to find new physics. It's just kind of like how it is. Yeah.
So your mentor discovered the fact that this happened, or was it that someone discovered that neutrinos change their types and then he implemented it into his experiment?
No, he did the theory. So he did the models and the calculations, and other people built the experiments, like Sudbury Neutrino Observatory and others. And so in the end, the people who discovered this, like, made the measurements, got the Nobel Prize in physics. But my mentor didn't get it, because usually it doesn't go to theory.
Oh, that's just, yeah, I know. That's actually a very common Nobel Prize problem, I think, right? That it's always the experimentalists who get the recognition, but that's just an unfortunate thing.
And you might know Art MacDonald, who's a professor.
Yes, at Queen's.
In Canada.
Yeah.
And he's the one who, he's one of the people who got the Nobel Prize for this some number of years ago.
Finite neutrino mass.
Yeah.
Right? He proved finite neutrino mass, which probably was integral for...
Well, his experiments demonstrated that neutrino change identities, and that they have mass, because he ran the Sudbury Neutrino Observatory. That's why. Anyway, I was just giving you an example.
Okay.
Yeah, he was the director. I was just giving you an example that popped into my head, because I love what you mentioned. I love how your professor gives you like the wrong theory, and you have to discover that.
Right.
But it's so special when it happens in astronomy and astrophysics and other branches of science, but it's very rare.
So in exoplanets, you don't really see that too often, then, is what? Because I would think looking at atmospheres of alien planets, I don't know, you might see something like, oh, that there's more nitrogen there than I expected, or something. I don't know.
That's not really new physics, though.
I guess, yeah, you're right. You're right.
I mean, the laws of physics and chemistry for like the world around us are pretty well established,
Right.
Like, if you want, because like our air, our atmosphere, temperatures and pressures that people have been thinking about for like hundreds of years, But I feel like there's some areas of physics, they're creating new temperatures and pressures that we aren't part of our everyday life. That's where I think there's room for new physics.
I get that. Now I kind of wanted to ask you on more of your specialty, or like finding the new Earth or the next Earth. I believe I read somewhere that NASA calls you the Indiana Jones of astronomy. So I guess I want to ask you, in specific to finding these Earths and whatnot, and finding these, planets, like how has your research been going in specific to you now? Like how's that been going? Well,
what happened, so just to sort of summarize like 20 years of work in a couple sentences before I get to what I'm working on now. So I worked on atmospheres, and I was one of, if not the first person to work on exoplanet atmospheres. And so I got to lay down a lot of the foundation of the field, because a lot of people didn't think exoplanets were real. They didn't think we'd ever be able to observe atmospheres. And we've observed like dozens and dozens of exoplanet atmospheres. So I actually was able to do a lot of the fundamental work in this field in terms of how to find atmospheres, what we should be looking for, how we should make models. So that kind of takes us up till today. And now most of my work with respect to atmospheres, it focuses on two separate things. One is the search for signs of life on other worlds. Here on our planet, we have oxygen. We all need that to breathe. But did you know that our atmosphere, it's filled to 20% by volume with oxygen? But oxygen is such a reactive gas, it shouldn't be in our atmosphere at all. So I love to imagine, like, if there's an intelligent alien civilization on a planet orbiting a nearby star, if they have Starshade and they're looking back at our sun and Earth and they see oxygen here, they'll be highly suspicious that there might be life here, because oxygen has to be continually produced. It's so reactive, it shouldn't be in the atmosphere. So it's kind of weird, because it wouldn't be, the Great Wall of China or city lights or pollution, not initially, but it'll be like oxygen, because life has re-engineered our atmosphere. But, on our Earth, we haven't had that much oxygen. Like, for most of Earth's history, we didn't have that much oxygen. So my team, we've literally been we're trying to go through every single possibility that could be a so-called biosignature gas in an atmosphere of another world. And what we found out is not pretty. And we found that, any gas you could propose, I could find a false positive scenario, like a scenario where you could get that gas without life. And it sort of like keeps going like that. But we've learned an awful lot, and we're just trying to be ready in case us or someone else finds an unusual gas. We would be able to kind of know what it is and what are the chances it's made by life. Because that's one of the main things I work on right now.
So I was going to say that the type of life that you're looking for is most likely going to be like non-intelligent life, right? Some type of bio signature in the atmosphere, instead of something like detecting like Dyson spheres or something like that around a star. It's going to mostly have something to do with the fact that something is simply alive on the planet.
Right. In fact, we wouldn't know. I mean, we might make the assumption that it's simple, single cell type life, but we honestly wouldn't know if it's intelligent life or if it's just some kind of slime, really. Because all we'll do is see what life does, not what life is.
So with all these false positive scenarios, do you have if I see this is what I can say might show? No, there's no like,
I think it's like you're getting to the very cutting edge of research right now. Because did you know for nearly 100 years ago, an astronomer realized oxygen could be a biosignature gas? James Jeans. And, I don't know exactly what he was thinking. It's just like a footnote in a textbook. But basically, he wasn't thinking of exoplanets, but, maybe he was thinking about Mars or, something like that. And so now we get to today, and it's no longer like a sure thing. And this is kind of really evolving research. So I don't want to like make anyone depressed right now, because I have my own kind of like, depressed is the wrong word, but it's like really upsetting to like think that we're not going to have something where we're like 100% sure, 95% sure, maybe not even 90% sure. Like we might be able to, argue, wow, this is so unusual. We don't know of any chemistry that could make this, but there'll always be that other person who can come up with something. And we don't know much about exoplanets. We have a mass and a size. We'll observe their atmospheres. But what about their crust? Like here on Earth, we have volcanoes and we have vents. A lot of complicated things are happening here. Did you take any geoscience classes in high school or university?
Unfortunately not, but we would love to listen.
If you want to work, okay, well, that's something that's what I would want you to do as an elective, honestly.
Yeah,
because
we have options for our geoscience courses. We do.
Okay. So maybe, I'd like to see the university allow people to take an elective that's another science class, because look, our Earth is so complex, but it's right here. And, we have subduction, like all I know about it, I didn't take one either, but as I was mentioning, I have kids who are either in high school or finish high school. And I learned something from there, from chatting with them about what they're doing. It's very amazing, all the things we know, but it's complex. Okay. And to like understand our atmosphere and what's in it and why, Like we're not 100% sure why we have so much nitrogen in our atmosphere. Like there's a lot of stuff out there. And so now think about an exoplanet. We don't know what's beneath the surface. We can't drill down. We don't know if the exoplanet has volcanoes, if it has plate tectonics so it can recycle material. And so all the false positive scenarios, you know, how do we rule them out, really? We don't know. So I think this is a TBD, you know, TBD, but it's going to be tough.
Yes,
So I was just going to ask, let's say you have like a very good measurement, very good proof that like, oh yes, there's no doubt in my mind that there is life on this planet. Then what, right? Like what happens after that? Do you just keep looking, or right, like it might be just too far most likely to go to, so then what do you do?
Well, in some ways I should turn that question to you, because if I get to see my dreams realized, find another Earth with Starshade, you know, see oxygen and water vapor and essentially an Earth twin, and I can be confident, although no one will believe it for sure, you know, that there's life there.
Of course.
Like that will take like literally the rest of my life. So I can answer that, but I'd like to put it to you because you're the next generation. So what would you do? Think about that. Yeah, you can think about that for a second.
I don't know what I would do, to be honest, because you could accept the fact and be like, okay, well, let's just look for more or something like that, right? Get more data points, or well, do you have any ideas?
I can't really think of something practical really to do, especially if half of these planets are, you know, a couple hundred light years away. Because the best way, as you said, to really determine this fact would be to go in the core, go in the crust, or, you know, do a little more research on the planet itself, being on the planet, you know, being 100. So basically, being 100 light years away. So there's just no way to really, I guess, confirm if there is life, even with these gases then. Like, so there's really nothing that we can do except basically make this ginormous catalog of information so that in the future, hopefully we're like, oh wait, if this happens, it's life. Oh wait, this was that planet. Is that mainly the purpose of what we're doing right now?
Like maybe. I mean, like I just say that. And by the way, so I kind of put you on the spot. So thanks for being a good sports about that.
Of course.
Because I've obviously had the advantage of thinking about this for a long time. So I can give you another answer. But maybe, like, sometimes we don't know what we're doing. I mean, that's what pure research is about. We get really motivated and really excited, and we don't always have an end game. And, you know, some people don't like that about pure science. But you have to sort of think of all the big discoveries that were made. Sure, a lot of pure science goes nowhere, but sometimes people hit upon something big. Like the insulin, you know, discovery in Canada. We have lasers that we use in our everyday lives, GPS. You know, there's tons of examples there. But back to this Earth thing. So one thing people will do is, you know, they'll want to do SETI, search for extraterrestrial intelligence, like focus in and listen, you know, put the radio telescopes, like focusing 24/7 on that planet. Maybe we'd send a signal. People are really against that. They're like, why let people know we're here? Or why let other aliens know we're here?
Right.
But believe it or not, but you know what? Because of your comments, I wanted to emphasize that some of us in this field, we're putting a premium on the very nearest stars. I mean, there's our closest set of stars that are 4 light years away.
Yep.
Which is still incredibly distant, right? But it's way better than 100.
Way better.
And so there's a sort of set of very nearby stars. If we get really lucky and there is a sign of life there, you know, there's a few things we can do. There's a movement afoot to send probes to the nearest star system. And it's going to take a while to like get this right. But the idea is to send up lots of tiny little space chips, little tiny chips that launch, that deploy a solar sail. It's a bit far-fetched, but the idea would be to put a giant bank of lasers on the ground. It would take up a square kilometer. And these lasers would go overhead. They'd have to be in the middle of nowhere where there's no planes flying over, and they would accelerate these solar sails to really high speeds. And it would take these maybe a 20th the speed of light. And these solar sails would go by, and just like when the little baby turtles are born, not all of them make it to the sea or survive. Not all of these would survive, but some of them would zoom past that star system, snap some images and send them back, and we could see some more details.
Isn't this also a popular Stephen Hawking thing? that Stephen Hawking was also involved in the solar, because you mentioned the word
Yes.
solar sail, and I immediately searched up
Right,
Stephen
right.
Hawking, and I remembered
Yes,
that.
it's actually sponsored by the Breakthrough Initiatives, and they've set aside $100 million to move this forward. And when they
Wow.
made their big announcement, Stephen Hawking was a part of it. That's right. Now,
That's
that's not going to
awesome.
solve the problem, but it's planted the seed for an idea that could move this forward. And I'll just mention one more thing briefly, and so, a lot of things in exoplanets, I just want to tell you one thing, is that there's this phrase I really like, and that is the line between what is considered completely crazy and what is considered mainstream. That line is constantly shifting. So when I started out working on exoplanets in graduate school, it was considered crazy. Like, why would people
100%.
fund this? Why would they spend time on it? It's going to go nowhere, right?
Mm-hmm.
But now that line has shifted because exoplanets is very mainstream astronomy, right? Oh my gosh, you're doing it in your class.
Yeah,
It's
exactly.
so mainstream. It's a class project. Like in 20 years, that's insane.
That's actually crazy to think about.
So now I'm telling you about this project called Starshade. You've heard about it, associated with Stephen Hawking. And it's kind of crazy, right? But just the fact that it's out there, it might become mainstream someday. And so there's one more out there concept I'll leave you with, and that is that people want to use our sun as a gravitational lens. They call it the solar gravitational lens. And if we could send a spacecraft really far away, 500 astronomical units, 500 times the Earth's sun distance, our sun could act like a lens if we lined it up right with that star, and probably a star at 100 light years would work even. And we'd be able to magnify that background planet so we could see something like 10-kilometer resolution on the surface.
Oh,
Wow.
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 And it's a lot more complicated than what I described. And again, this concept is like 20, 30 years away, and it would take 20 years to get to its lined up position. And you'd have to have one telescope per planet of interest, planetary system of interest, because it has to be lined up.
Yep.
So there are some, what do we do next? There are some ideas, but they're just going to take long time. But there's something that I hope that people your age, will see sometime in your lifetime.
There's some very exciting stuff.
Very exciting stuff. I wanted to inquire a little deeper into the life of in other planets. I'm sure a lot of our viewers are familiar with the Drake equation. Maybe we can go into the Seager equation. I believe you have kind of maybe you can describe it the best. What have you exactly done to the Drake? Maybe a little introduction on the Drake equation, what you've done to it to make it what it is today.
Sure. Well, the Drake equation, it's really a series of terms, less than an equation, which helps to illustrate the search for intelligent life. And the Drake equation has various parameters. So you could make your own estimate kind of about how many, I hesitate to say what's the likelihood that there's an intelligent civilization out there trying to send us a message. So the terms in the Drake equation, for example, are like, what's the star formation rate in our galaxy? How many stars have planets? What's the, fraction of those planets that have intelligent life, that have the capability to build radio telescopes? And so it kind of serves you as an illustration of what the search for intelligent life by way of radio signals they might be sending us, what that involves. So I took the Drake equation and I redid it to illustrate our search for life by way of signs of gases in an atmosphere that don't belong, that could be attributed to life. And just like the Drake equation, the first few terms are things we can actually measure. Like we can choose the number of stars in our sample that, for example, Starshade would have access to. We can ask ourselves, what's the fraction of rocky planets? What's the fraction of rocky planets in the so-called habitable zone of those stars? And so the first few we can actually put a hard number on. But just like the Drake equation, the last few, we can't answer those. We can't put a number on them, but they're there to serve as an illustration of what's involved. So one of the last two terms is, what fraction of those, rocky planets in the habitable zone have life? And then the last term would be, what fraction of those planets with life is producing a gas that has a spectroscopic signal we could detect from afar? So it kind of lets you play around with the numbers to just kind of see, how lucky do we have to be to find one? Like, does every planet need to have life? Or, does all life need to be generating a gas that we can see from afar?
So do we
So that's
have?
the Seager
Yeah,
equation.
sorry.
Yeah.
Yeah. So do we have any ideal? I shouldn't say ideal, but guessing parameters like for these unknown terms. Do we have any? No,
No.
no way of guessing
Like,
even.
no. I mean, we just, how many planets have life? No.
Because they're just probabilities, right? So I would think. I mean, I guess not right now. Yeah, I guess right now we're still too young in the field, but maybe as we get to know more about gases, it's just a probability statement, right? It's not really
Sure.
there are 5 in these 10. It's just a probability
Right, well,
there might be.
Yeah, and it's really not even a probability. It's more like a fraction. But
Yeah,
sure,
fraction,
but you
sorry,
can make
sorry.
your own guess.
Yeah.
So the goal, right, we're all allowed to speculate, right? For me, I would just put a 1 there, like 100%,
You could.
That would be my guess there. But I did want to tell you that I met Frank Drake a couple of times.
Oh, wow.
And one time I met him, it was like a celebration. I think it was a celebration of his, I want to say it was his like his birthday. It was like his 80th or 85th birthday. And he came here to the United States, to the Boston area. And it was hosted by Harvard University. And they chose like one scientist to talk about each term in his equation for like 5 minutes. It was like, then there was like a celebration. And so I took that opportunity to ask him, I hope it's like, it was too late, of course, but it's like, I hope it's okay with you if I took your equation and kind of rewrote it, just to make sure to like cover my bases.
That's
and
so
he
funny.
said, sure, that's fine.
So you have his blessing.
I have his blessing. Yeah.
Yeah.
But it's one of
that's
those
very
things
sweet.
where I didn't have the chance to ask him in advance, but it was afterwards. I hope you're okay with this kind of statement.
Lastly, I believe there are some interesting points on Venus that you wish to share with us that I would be more than happy to listen to, because what is Venus? Or like what's so special about Venus, I should say. Not what is Venus.
Well,
what's so special
let me start
about
with
it?
the back. So what's so special about Venus is it's right next door. It's like kind of like our evil twin planet. It's about the same size and mass as Earth, but it has a massive carbon dioxide greenhouse atmosphere. And the surface on Venus is 700 Kelvin. It's too hot for life of any kind, like period, unequivocally. What's really interesting about Venus is just like here on Earth, as you go up above the ground, like if you ever, I know there's no mountains in Ontario, but if you ever hike up a mountain or you go in an airplane, like the temperature drops as you climb. And that's same on Venus as well. So that high above the surface, about 50 kilometers above, the temperature is actually just right for life. And so that led Carl Sagan to half a century ago speculate that perhaps there's life on Venus, not like we have on here, like mammals and complex life and trees, but microbes floating around in the clouds. Now here on Earth, we also have life in our clouds, small microbes that get swept up by winds and they stay up there like for a week or so. And unlike on Earth, how we have clouds that are fragmented and come and go, Venus has like a permanent cloud cover that's very extensive vertically. So the issue is now that the clouds and the cloud layer, it's an incredibly harsh place for life. These clouds are not water, but they're concentrated sulfuric acid. Very bad, way more acidic than any environment on Earth. No life we know of could survive in those droplets unless it has created a shell of material like wax or sulfur, other other concentrated sulfuric acid materials that resist that acid. So let's fast forward to a few years ago remember how I told you my team's going through every gas that we think could be a potential biosignature. And we came across a very interesting gas called phosphine. That's a phosphorus atom attached to 3 hydrogen atoms. Now here on Earth, like on Venus, we don't have too much hydrogen, and the temperatures and pressures don't favor phosphine to form. It's really hard. You need a lot of energy to form phosphine. Yet here on Earth, we have incredibly strong evidence that life on Earth makes phosphine. It's only associated with life on Earth. Oxygen-free environments like wetlands, animal guts. People see it in their laboratory studies of mixed cultures of bacteria. It's made by humans as like pesticides and things like that. So unbeknownst to me, across the ocean, another professor, Professor Jane Greaves, was working on phosphine as a potential sign of life. But she purposely set out to search for phosphine in the clouds of Venus as an indicator there might be life there. Now, as scientists, by the way, we have like a research portfolio. Think of like a pie chart where some of your research is pretty plain and it will deliver. And some of your research can be very high risk, high reward. So because we were working on phosphine as well, a mutual contact connected our two teams. Because we had been researching phosphine, thinking about how it looks in the atmospheres and how life makes it, well, we had a ton of info. So we got to work. We were really lucky that we got to work as part of Professor Jane Greaves's team. Well, after several years of taking data with 2 different radio telescopes and with a lot of hard work, we reported the discovery of phosphine on Venus.
Wow.
And yeah, along with our discovery, we had like calculations of chemistry on Venus. And we wrote that out of all the chemistry we know that might happen in volcanoes or lightning or meteorites hitting Venus, everything we knew about chemistry and about Venus, that these processes might generate a tiny bit of phosphine, but not enough to match the observations. And so that's a sort of fundament of biosignature gases, is if you can't find a way to explain it with like chemistry, then it leaves room for the possibility that there's life making phosphine. And that was like an announcement in September 2020.
Yeah, I actually remember this. So wait, so were you a part? So you were a part. So your team was a part of this announcement? Yeah. Oh wow. Yeah. Okay, because this was so this is like a very recent discovery.
Yeah, and so if you want to go back, you can see that the 3 people who made the announcement were myself, Professor Jane Greaves, and Dr. William Baines, and we had like supposedly 30,000 people were watching this online announcement. Which, okay, that's not like the Super Bowl, but that's, wow, huge for science.
Incredible.
For science, it's incredible. It's absolutely incredible.
Yeah, so I wanted to share with you what's happened since then. First of all, people immediately didn't believe it. People were very skeptical, and people were angry. You know, we have social media. I'm sure you folks are on Twitter and other things. People started blasting us with like, oh, it's volcanoes, or it's this, or it's that. And there's a sort of level of like anger that I just hadn't anticipated. And then the data from all these large facilities, the telescope was ALMA, Atacama Large Millimeter Array, a big radio facility in Chile, and the James Clerk Maxwell Telescope. You know, the data is public because these are like large taxpayer dollar facilities. ALMA's an international. And some independent teams looked at the data, and some of them didn't recover the signal at all. So that's tough because you want your results to be reproducible. And this was like a very, very tough data analysis. It's kind of like what we were talking about before. Remember, if you have a really small planet and there's a lot of other noise sources, how do you analyze the data to like get that signal to pop out? And so that caused a lot of controversy as well. And it's still a controversial measurement. But every time there's been a published journal article that analyzes the data in a way where they don't recover the signal, our team led by Professor Jane Greaves comes out with like a rebuttal saying, in fact, we can change the way we analyze the data to your way. We can do this, we can do that. And we still stand by our original report that there is phosphine there. But bear with me for a minute, because I'm going to circle back to exoplanets, okay? The second thing people complained about was they said some teams actually did recover the signal. So people are kind of in disagreement. And they recovered the signal, but they said it's not phosphine. It's got to be sulfur dioxide, which is a gas that's known to exist on Venus. It's been measured many, many times. It comes out of the volcanoes. And so it could be because there's one overlapping spectral line of like a very weak sulfur dioxide signal. But thanks to Professor Jane Greaves, she discovered that an observation had been made just like a few days before our observation, purposely of sulfur dioxide, but at a different wavelength, a different frequency. And we were able to argue that it's not sulfur dioxide because sulfur dioxide would have to have increased by a factor of 10 in just a few days, which is really unlikely and unprecedented. So we can argue that away. Anyway, so there's like many, many papers in the literature, and this is how science works. Someone reports something, someone disagrees. It goes back and forth and takes a very long time. But my comment about exoplanets is when we find a sign of life, like a biosignature gas, first of all, people might disagree. They might reanalyze the data. It's going to be a tiny signal. You know, other people might believe a signal, but not the attribution of the signal to a given gas. And we know a good amount about Venus, okay? There have been like a dozen or more probes into the Venus atmosphere in the 1970s and 1980s. We've had several orbiters around Venus. Like we know way more about Venus than we ever will about an exoplanet. So that's partly why before I was like, it's going to be really tough because people come up with a false positive when we don't know much about it. Because on Venus, the thought that phosphine is a sign of life, it's still out there, but it's been very much like trashed by a lot of the scientific community.
That's I mean, it's always a debate, right? With anything
It's a
that
debate,
gets
right.
that gets discovered, and
Right.
like you definitely stand by your original measurements, and
We stand by our measurements, but what's really interesting is Venus is really nearby. We could imagine returning to Venus with probes that search for phosphine. And once you're in the atmosphere, it's much easier to look for it than, from afar for like a variety of different reasons. So you don't have to feel too bad right now. Like there's always ways around this. And there's actually, so one more thing that's kind of related is there's been a discovery of methane on Mars about 15 years ago. People used telescopes on Earth and they found methane on Mars. And that's very unusual because Mars doesn't have a lot of hydrogen. So any carbon, CH4, you kind of expect it to be with oxygen, like CO2, or maybe some CO, carbon monoxide. It's mostly carbon dioxide. And no one believed this for years. It kind of went back and forth. And then there's orbiters. One orbiter has seen methane. There's a lander, a rover on Mars that has measured methane. And there's still like a holdout of a small group of people that still don't believe it.
I don't
They're
think you
like,
can
it's
really argue with that.
Yeah, I mean, SpaceX
All they say
is
is contamination.
Yeah.
They want to argue it's contamination. It's not really from the environment. I mean, I don't know. There's always an argument.
Right.
But I think it's pretty much established now. Methane is not necessarily associated with life because it can also be made through other geological processes. But that was like 15 years or more to kind of get that story. So yeah, stuff takes a long time. And we'll just have to see where this goes. So I'm hopeful that we definitely, so on Venus, it's this whole phosphine discovery, by the way, it's led to a huge cascade of events, possibly including NASA selecting 2 missions to go back to Venus. The European Space Agency has a mission going. None of these are measuring phosphine or studying life or habitability in any way. But I've been leading some mission concept studies to go to Venus with very small private focused missions to search for habitability and signs of life. And that's one of the main things I'm working on right now.
I think looking for life on nearby planets is the most like feasible option at this point, if for like clear evidence that there is life elsewhere than on Earth, especially because we can literally send probes to these planets.
Yeah, I guess that definitely helps with the whole process because the closeness definitely helps. But I think it wouldn't. It's not in our Goldilocks zone though, right?
No.
Venus it's off the Goldilocks zone, right?
Yeah, I mean the Goldilocks zone is a bit oversimplified.
Yes, for sure.
You can think about other planets like Titan is very, very cold, or other moons rather. Titan's one of Saturn's moons that has liquid on it, not liquid water, but liquid ethane and methane lakes. People want to search for life there. So we definitely have to think about it being like planet or moon specific.
You're also currently involved with many projects such as like tests, like the exoplanet space telescope and whatnot. That's also looking for similar things, right? Outside of our solar system.
Right. I'm actually not involved with tests anymore because I stepped down once the prime mission was over, and that's when I started working on Venus.
Oh, okay. Sorry, what was the prime mission?
Well, the TESS prime mission was the first 2 years of the mission. The TESS, like the prime mission, that was the first 2 years where TESS looked at the southern hemisphere night sky first and then the northern night sky. And like the mission was initially selected and funded for 2 years. And so then it gets renewed, so once it sort of had completed its initial goals is when I stepped down, but the mission's going on because the telescope will keep working and it gets renewed every few years.
Okay, so well, I mean, hopefully Venus tells us or shows us some good signs. I know I remember the sketches. I don't know if this was in Cosmos or if it was just like an animation, but like those cloud cities in Venus, You know, with like those covers. I think because I think that's the theoretical or hypothetical idea, right? Because as you said, the upmost atmosphere is relatively okay for some certain life. So let's see where it goes, right? I guess that's our only next step.
Right. Well, yeah, it's been awesome having you on the podcast today. Thank you so much for agreeing to this this episode.
Is there anything else you would like to say? Anything you want to tell our listeners? Anything else about what you do, or are we content?
We're content, and you've done a fantastic job.
Oh, thank you.
Thank you
so
very
much.
much.
Again, as Parker said, thank you so much for coming on today. It was really lovely to speak to someone. I don't think we've ever spoken to a professor not from you, have we?
Yeah, we have. Yeah, your research.
Oh, yes. Sorry. Oh, but I should say, okay, then let me say American professor. Let me say that,
Sure.
because I don't think we've had that on before. So you were our first on that. So thank you for being that. Thank you for coming on today.
Right.
And yeah.
If you are listening to this episode right now, make sure to like and follow the podcast. Rate this podcast 5 stars on Spotify.
Why not?
And make sure to leave a comment if you want to be comment of the week. Next week.
Also check description below. Everything that Professor Seager was mentioning will be there, or at least like the broadened topics, like, quick links and quick mentions that you can just search it up, because I think a lot of them even we will search up personally afterwards. So have fun on that. And yeah. Thank you for listening. Thank you for watching.
This has been episode number 99 of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we will see you soon.
Bye, guys.